Okay, I just want to say a few words in general before I start this lecture. Well, my name is Antonio, and feel free to interrupt. And as Fernando did, I would like to make this a two-way conversation. And here's where I think I have to maybe apologize. Well, you will see. I was told that none of you, or a small minority of you, would know much about computers and informatics and networks. So I actually put together. I wanted to structure the series of lectures as well. I'll start with even an undergraduate lecture on computer networking, and from some of the questions from you, I guess. Maybe you'll kick my butt on these things. We'll see. I know something about networks, but hopefully you will not be bored. So anyway, I wanted to structure the first lecture as a review of traditional networking. So really, this is going to be pretty much a lecture that actually, let me ask a quick question. Who does not have a bachelor's degree in informatics here? Or 1, 2, 3. Oh, okay. Computer engineering? Okay, and then maybe tomorrow or next time we'll see. I'll go into more researchy presentations to tell you what I do besides teach computer networking. Okay, so I wanted to give a lecture on networks, and I didn't know what to do. And the lecture, then I decided to focus on the transport layer, because it's the layer in traditional layering architecture that I think is more interesting from the viewpoint of algorithms and a little bit of math, arithmetic, not really math. Okay, so let's get started. You know these things, so why Okay, so there's this thing called a web browser, and it talks to another thing called a web server, and they exchange these these weird things. The thing, it says get Carzaniga, and then if you do that, and if you're connected to the Unisi website, then you get my webpage. But sent on the other end. So this is an application level protocol, and you all know what that is. Now the interesting thing is that you can open a connection, a TCP connection. Everybody knows what that is, and send a lot of those requests, and these things are interpreted by the server, and server responds. So at the application layer, when you program these objects, you have the illusion of having a pipe, okay, where you can send streams of data back and forth. You can write get is character G in ASCII, which is an encoding of this thing. It's 8 bits, whatever that is. I think it's 70 something. In reality, you don't actually send these streams. It's not that there is a connection. There isn't a tube or a wire that goes from my computer to Google, somewhere in California. There isn't such a thing. So in reality, my computer sends these things, these packets. So the information comes in these quanta of data. So you send those things, and hopefully they get to the other end, and then the other end sends other such things, the packets back. Now you think that that's the situation. Actually, that's not the situation. The situation is even more complicated. There isn't a single wire that connects. The computer is connected to another computer, usually called a switch or a router, and that router is connected to another router, and that router is connected to another router, and all the way through. How much would you guess is the hop count between here and Lugano? Actually, I didn't check.
14.
Huh?
14. 14?
If you mean every hole, which is returned by the trace route, for instance.
Wow, you actually tried. No, you made it up. You pulled it out of the... Okay. Yeah, it is 14. I tried. I was on the plane, you know. I was on a plane. I'm coming straight from Lugano. In fact, that's why. Sorry, I didn't have a tie. I stopped being a clown. No, I'll never stop. Okay, so in reality you have this is the situation. So a network actually looks like this. This is obviously an oversimplification, but you have these bubbles here, they're called routers. They have physical interfaces, and those are actually wires. Well, the informed people here say, no, they're not. But let's assume that they are. At this level, yes, they are wires, and there's some packets that find their ways from sources to destinations throughout the system. This is pretty much what the internet looks like. And they find their ways because the routers make routing decisions. Actually, they make forwarding decisions. And the forwarding decisions can change. So you can have one route one time and another route another time. In fact, if you have one route one way, do you have the same route the other way? Maybe, maybe not. Not necessarily. Okay, so it's a complex system, and to make those decisions, routers have to be very fast, and they have to have data. Okay, that's all very interesting, but I'm not going to talk about that in this lecture. In this lecture, I'm going to talk about the transport layer. So again, we have a packet switch network, and I'm going to fly through this because you all know this stuff. You know what best effort means? Oh, you should know.
What do you mean by best effort? The best efforts of a transport layer, or what?
No, I'm talking about the network layer here. So I am talking about the term datagram network. Okay, so the term datagram network means essentially these three things. It means, number one, that the network is a packet-switched network. Okay? If you don't know what that is, we can spend more time. But as I said, the lecture was supposed to be about transport. So I'll move very quickly through this. It's a connectionless service. So you put a packet in the network and the packet goes. You don't have to set up a connection with the destination, which is what you do if you make a phone call. When you make a phone call, this is a connection-oriented service. You dial, there's a lot of signaling. You establish the call with your friend and then say, okay, what are we doing tonight? Should we go eat pizza? Okay. Instead, the network on the internet is a datagram network. It's a connectionless network. And another aspect of the term datagram, this is just terminology, there's nothing profound about it, is the term best effort, which is kind of an interesting choice of term. Best effort, you know what that means?
It means that it can transport your packet, or it cannot, but it will make its best effort.
That's a good characterization. That's the optimist characterization. The pessimist would say best effort means no guarantee. There you go. In fact, it means nothing. You got nothing out of this network. So how much do you pay per month here for network connectivity?
$30.
$30? Okay, this is universal. I paid 45 francs in Switzerland. Okay, for nothing. No. But there's no delivery guarantee. There's maximum latency guarantee. Nothing. Bandwidth guarantee. Yeah, nothing. So that's a datagram network. Okay, the point of this is a very unreliable substrate. It's a base that is very flaky. Okay, it doesn't give me much. So what is the transport layer? Well, the transport layer is the magic that on top of this very flaky thing builds something reliable. So it does some things that we don't care about. It does reliable data transfer. That's what it does. And primarily today we talk about this: integrity and ordered delivery. which also means streams, as I said, connections. It does also another fundamental things, and maybe if we have time, I don't know, because I have a lot of things to talk about. Maybe we'll talk about congestion control, which is another fundamental piece of the transport layer. Congestion control is what actually makes the system not blow up, not crash. Okay, in the early days of the internet, the internet didn't have very good or any mechanisms for congestion control. And then at some point it really collapsed because of congestions. So congestion control is now in place. So anyway, today's lecture is just a cap. Today's lecture is about transport. So how to go from something like this, packets, to something like this, a stream. A stream is reliable, more reliable than packets, let's say, and in order. So things go back and forth. Okay? That's what we talk about today. So from unreliable datagram to reliable stream. That's the topic of today's lecture. So you're all mathematicians, so I'm kind of I'm not going to. You all know what finite state machines are, so I'm not even going to talk about this example. Now it works better with examples. What is this example? I think it's called.
Something like a switch.
It's something like a switch. I think it's called a flip-flop, right? Actually, I don't see any switches here. In our classrooms, we have exactly that switch. So it's one button, and you switch on, switch off. Okay, this is what this is. Same signal, on, off. Boring. Okay. This is another example. Much better example. Here's another example. This is a flip-flop, but it's a set-reset flip-flop. So it's a flip-flop that has two signals this time, two inputs. The set and the reset. So if it's in the 0 state and you set it, it goes to 1. Okay, so you should complain right now. I told you, let's make it interactive. You can say, we know this. I like this one. I like this one. So I'm going to do that. Actually, I like the following one better, so you'll see. What is this?
Lock, maybe, or something like that.
Lock? Yeah, the word lock is. It is, I don't know. This is. I am self-centered. Everything I do, I think everybody does the same. My phone has this locking mechanism that you press a button, and then if you quickly press another button, it locks the keypad. Okay, so if you press one button, it's in the I'm wrong. It should try unlock state. If you're in the unlock state, this is what kind of example? It's wrong example. You try to unlock it, you have to press another button very quickly, and so it goes into the unlock state. And then if you wait 30 seconds, it goes back into the lock state. But if you press the button and don't do that within 1 second, it switches back. The important point of this example is that in networks, we'll see the whole point of showing you a finite state machine, which we all know, is that these things are useful to define network purpose. And so this is a good example because it has timeouts also. So here's my favorite example. In fact, one of the first ones when I studied. I also come from an engineering school, and somebody presented this to me. What is this? Huh? A tennis match. Yeah.
Like that.
It looks exactly like that, right? So that's a starting state. Point A. Player A. 15, 0, and so on. And then the real serious mathematicians in the room will notice that there are some states that are indistinguishable. Which, if you play tennis, you know. I mean, if you play tennis and are a mathematician at the same time, then you know that why do they call 40-30 different than advantage A? Why? There's absolutely no difference. You thought about it?
Yes.
Okay. Well, think about it tonight. Okay, so the point is that these things are useful to represent protocols, and in fact, we will use them in this first part to represent protocols with this notation. So we'll have every edge, states are states, we'll call them by their name, and we'll try to make it meaningful. And edges have two labels. On the top, we have the input or the message received. And on the bottom, we have the output or the message produced. Instead of the message received sometime here, we might have a timeout. Or instead of the message produced, we might have nothing because we produce nothing. We just switch state. Okay? So, this represents a conversation. So I could be using this state machine with you or with myself. So I could be in state S. I start to say S, and I would say hello. There you go, yo. And then I say blah, blah, blah. And if I shut up for 30 seconds, okay, I just gotta say bye, okay, bye. So this is serious because serious guy. No, because we can actually represent actual protocols. Do you recognize this protocol? Well, the title says it already. So SMTP, it's actually a subset of SMTP, which is a relatively complex protocol. It's the protocol used by mail servers. So you start in state S, and the first thing the server does, the server accepts, this is the server side. So this is the server side of the protocol. The server accepts typically a TCP connection, and it replies with a message that says 220 OK, or 220 OK. And then in this accepted state, you can tell the server, the client tells the server, recipient 2 sends the recipient 2 command, and then the server replies OK, and then says the mail from command, and then it waits for the data, and so on. So this is we use finite state machines here to specify transport protocols. Okay, let's go back to reliable transfer. What is reliable transfer? Well, it's playing games. It's a trick. You try to trade a little bit of time to acquire a little bit of reliability. So you spend time and you get reliability. Okay? It's a program. It's an algorithm that sits in the middle between the applications and the unreliable network. So the architecture is like this. There's a best effort, which means no guarantees at all. And what we talk about today is these two algorithms, these two boxes. Okay, they speak to the application back and forth here, and they speak to the network back and forth here, and they add something. They add reliability by spending time, effectively. How do they speak? Well, this is just terminology. I'm going to use those terms. It's not that you will find those terms in your computer necessarily, but just so that you and I can understand. This is when the web browser asks the transport layer to send some data. So it calls reliable send. So it tells the transport layer, please send this data reliably to the other side. And reliable receive is the other way around. The transport layer says to the application, hey, there is some reliably delivered data for you.
What's the difference between reliably delivered data and simple data? Why do you need this R_scope reference for a simple?
Well, guess what? Because underneath that there's going to be an unreliable send and an unreliable receive. It's just to distinguish these two. This is called by the network to the reliability service, to the transport. And this is called by the transport to the web application. So, if you call reliable send once, maybe this is going to call a lot of unreliable send, and it's going to do a lot of unreliable receive, and then at some point, maybe it will call once the reliable receive. Okay? It's just to distinguish the ones that are between the transport and the application, and the ones that are below. And obviously those two things are connected to the other side. So every time you call unreliable send here, maybe, maybe not, maybe in a month, no, not in a month, but maybe in 2 seconds, some packet will show up on the other side. Okay, so this is the architecture. In reality, this thing is called also a duplex channel, because you see the communication going one way and the other way. To make things simple, just for the purpose of discussing the protocols, we talk about a simplex thing where we have the sender side, and the receiver side. So we explicitly have the sender side of things, and we have a different algorithm here, the sender side of the reliable transport layer, and then the reliable receive on the receiver side. Okay, so there are two different algorithms. Okay, is this clear? It should be pretty clear. Okay, let's look at what you might call the dumb or useless, stupid, use whatever derogatory term you wish, algorithm or state machine. This is it. The sender receives a call from the application. Please reliably send this data. Turns around and sends it to the network. On the receiver side, every time the network receives something, sends something to the receiver ships it to the application. So does this work? Well, it works only if the network is reliable, because otherwise we're not adding anything. We are wrapping the unreliable things with something that we call reliable, but it's not any more reliable, right? Because we're doing anything we're told to do here and here. So in this particular case, if this thing fails, then communication fails. If the receiver receives the same data twice, it will give the same data twice to the application. So that's bad. Okay, it's just to show you how things work and how we connect the state machines with the architecture that I was showing before. This is all clear, right? Okay, so let's do something concrete, something real. As Fernando did, we will start by modeling the objects we have. So we will assume in the first case what we call the noisy channel. A noisy channel is a channel, a communication network, that can introduce errors but does not lose packets. So in this particular case, we introduce errors in the sense that some of the bits in the data might be flipped. You send a 1 and the receiver gets a 0. You send a 0 and the receiver gets a 1. But all the data gets there. And now I'm going to ask you, how do human beings deal with this kind of noise in the channels?
Repeat.
Repeat.
Yeah.
You used the right term.
Human beings. Human beings use the CRC.
CRC, yeah, I do this all the time. No, natural language.
To ask to retell.
What's that?
Ask to retell.
Yes, but before that, what do?
Verify the result and try to guess what.
You verify the result. Try to guess. Okay, we're in the right direction. Okay. So speak louder. Like those old folks on the phone. No. the idea is that human beings use natural language. And I don't know if you ever realized this, but natural language is very, very redundant. The signal sends a lot more bits than the actual content bits. Not just because maybe I'm blathering and not saying anything useful, but because even the useful things that I say take a lot of bits. One, because the channel between my neurons and your heads is noisy. You know, my ear, it's gone a long time ago, playing guitar too loud. My mouth, I make mistakes. I'm speaking a language that is not my native language. You are certainly most of you are not native English speakers, so there's also the understanding part. So what do? You use the extra bits that are in this very, very verbose means of communication, natural language, to do something that mathematically or in communication theory is called error detection. So there's an error detection code. The sounds are designed, or the speech is designed so that you can understand that you didn't understand. In fact, somebody who doesn't speak a language very well has that dilemma many times. Am I not understanding, or I'm not even at a point that I don't understand that I don't understand. And believe me, I've been through that phase too. I lived in the US for a long time, and at the beginning, I couldn't understand anything. Not even the fact that it was a word that I didn't know, or that I couldn't figure out the sounds. So if somebody speaks very quickly to you, you don't know that they said something that is a term that you don't know. Even if you read it on paper, you wouldn't understand. Or you just didn't get it. You know? So people do error detection. So the first step is error detection. And the second, you have a question? No. And the second step is receiver feedback. So you're on the phone, you know, something, and what do you say? What? Repeat. Excuse me, please. All those things that I said. Please repeat. So feedback to the sender, and the sender then retransmits or speaks louder. So error detection. I don't need to bug you with that. I already gave it away. For those of you who didn't read it, what's the easiest example of error detection? Huh? The pairing bits. Huh? Hamming code, exactly. That's a sophisticated version of Hamming codes. Exactly are they're also error correcting codes, right?
Exactly.
Anyway, or CRCs or checksums, all those things. They're error detection codes. It's a code that you send along with the data, and there's an algorithm, a known algorithm that takes the data or presumed data and the code and says no or yes. Okay, it says no errors, yes errors. So parity bit, I'm not going to give you an example because you all know what that is. Okay? So in my notation, we're going to have this notation here that says there's some data and we're augmenting the data, adding something to the data. We're adding an error detection code to the data. We're going to represent it with this, square brackets and with this little star. Okay, so that means I'm sending you some data with an error detection code. So here's a sender algorithm. The sender side of a transport layer that uses this. Okay, it's intuitive. Hopefully, we start from the first state S, and whenever the application tells us to send some data, we create a packet, a data packet with the error detection code in it, and then we send it, and we go into this app state where, guess what, we're waiting for an acknowledgement from the other side. And if we receive a packet that is a negative acknowledgement, which is the feedback we were talking about before, right? When you talk to your friend on the phone, you say, let's do this. Don't talk to him on the phone. Good example. But it's for me. And the packet is a NAP, meaning it's negative feedback. It's somebody telling you, excuse me, I didn't understand. Could you please repeat what you just said? Then you resend the same data. So you repeat again. If it's a positive ACK, those things are positive ACKs, right? Then you go back into this state. And then you let the application send again. That clear? Yes? What about the receiver? The receiver is a little simple. It's simpler. In general, the receiver in this topic, they're simpler. The receiver does two things. If it receives a packet and the packet is good, so the receiver checks the error detection code. And if the error detection code says, okay, then it sends an acknowledgement and it delivers the packet to the application. If it receives a packet and the packet is corrupted, which again it decides based on the error detection code, then it sends a negative acknowledgement and it doesn't obviously communicate the data to the application, right?
And what do we do if acknowledgement packet is kept as well?
He's stealing my punchline. So the next question was, does this really work? And you already know the answer. The answer is no, it doesn't work. Why? Because what happens if the ACK or NAP is affected by an error? Okay, so in that case, what do?
I resend the packet and
right. So you go into this loop. This is one of the various examples. The sender says, let's go see taxi driver. Taxi driver? No? Who has not seen Taxi Driver? Only he hasn't seen Taxi Driver. Taxi Driver, great film, Martin Scorsese. And the receiver hears something that is noisy. Okay, let's a taxi. Maybe let's go take a taxi. Receiver says, repeat message. And the sender hears noise. And again, we're in the same loop, right? So this doesn't seem to converge or end to something. Eventually, it might. Okay, but it doesn't seem like a great idea. Another approach, is to make the acknowledgement or negative acknowledgement so redundant that it would be impossible for that to be mistaken. So you yell, yes! I heard it. This might be a good idea because if it's just an ACK, but it also might be a bad idea because in networks maybe some errors come in bursts. So it's not true that if you make it really, really long that you're protected against all possible types of noise. One other approach is this. Let's consider this for a second. Assume that it's a negative acknowledgement. So anything you hear from the other person is either correct, or if it's correct and it's a negative acknowledgement, or if it's incorrect, you assume it's a negative acknowledgement. You understand the point, right? So if you hear noise, you assume that it's please repeat. Okay? And then you repeat. Okay? Does that work? It does, huh? It doesn't. Come on. How do you deal with duplicates? It generates duplicates, right? If you send a packet gets there correctly, and the receiver sends you a positive acknowledge, and you hear noise, you interpret that as a negative acknowledge, so you resend. He's stealing my lines too. Must have studied my presentations. Sequence number. So the way you deal with repeated messages is you let it know that they're repeated. So you give them an ID, and then the following message is going to have a different ID. Essentially, a counter would do, right? Count 1, 2, 3, sequence number. So if you say, let's go see taxi driver, you say 7, let's go see taxi driver. And the receiver here is 7, let's go see taxi driver. So it passes, let's go see taxi driver to the application. Okay? This is sender and receiver here are the two things in the middle, remember. Passes this message to the application. And then it says, got it. Okay, thank you. And then the sender hears noise and then resends 7, let's go see taxi driver. The receiver hears 7, let's go see taxi driver, and then ignores the packet this time because it knows that it already delivered to the application data packet number 7. So we don't need to do that. We don't need to do that.
Shouldn't it send the egg after it? I guess it should.
It should. It should. Yeah. Let's see, did I do it? No, I didn't. Oh, no, but it should. Absolutely. In fact, maybe you should also say, yeah, I got it. All right. You know, maybe a little. Okay, here's an interesting question. Remember the protocol we were looking at before? The one that you send and wait for the acknowledgement. Send and wait for the acknowledgements, right? Now we have to add a counter. So you say 1, blah, and somebody says, 2, blah, something else. And how many bits do I need to represent the blah that I send? How many bits in this protocol?
Well, for this
1 bit. Why?
Because we will just use.
Exactly. So you need to distinguish the current packet from the previous one. That's the only thing you need to do. You need to distinguish what I'm waiting for right now from the one that I already received. So let's call one. We call it 1, and the other one we call it 0. So this protocol is called stop and wait, and it's represented by this finite state machine. We start in state 0. We produce a data packet, so the application sends us some data. We produce a data packet that contains the sequence number 0 and the data, and it's all error correction or detection protected. And we send it, and then we wait for acknowledgement 0. So if we receive a packet that is corrupted, it's okay, we resend it. And if you receive a packet is good, and packet is the acknowledgement, we go on, right? We go on to S1, where the next data is going to produce with sequence 1. So, if you actually look at this, doesn't this look familiar with the previous one that we looked at? Do you see a relation between this state machine and the previous state machine? Remember? Why don't you try to collapse these two things like this? These two things and these two things. It's the same, right? Because it's going backwards. The only thing is that we're now distinguishing state S1 from state S0 by the bit that we add to the data. So the counter is going to be 0 or 1. Okay, great. So we have our first protocol. Does this work?
It works better.
It works better. It works better. Politician? What about the receiver end? Again, this looks exactly the same, right? Remember the previous machine, the previous finite state machine, the receiver side, it had only one state and had the 2 ears in this one state, right? Now we have the 2 states. In one state, we're expecting sequence number 0. Is that this? Yes. No, we're expecting sequence number 1. No, we're expecting sequence number 0 here. And here we're expecting sequence number 1. So if there's no errors, we keep going back and forth here. We receive a packet with sequence number 0 and go expecting sequence number 1. We receive sequence number 1, we go back. If we receive again sequence number 1, we just resend the acknowledgement, which answers your question. I'm sorry, I can't see you when I do this, but right? Is that clear? Okay. And yes, it works. It works under that particular model. Okay, so it works under a situation, an application, a channel model that is noisy. So there's errors, but no losses. Let's skip this one because it's. So this is effectively the protocol. I'm just going to replay it, but you understood it. So you start from 0. If you receive data from the application, you put it in a packet with sequence number 0, send it, and then wait for acknowledgement. If you receive the acknowledgement, you move to the other state. In the other state, if you receive data from the application, put it in a packet with sequence number 1 and send it. Receive the acknowledgement and go back. Okay? So the circle is the situation where you have no errors. If you have errors, then you start resending things. So if you are expecting a specific acknowledgement and receive the other acknowledgement, then you simply resend. And similarly here. Okay, they're symmetrical. The only difference is the sequence number. Okay. So what about losses, packet losses now? Can we make this also resilient to packet losses? Yes. The answer is yes. Okay, I'm not going to talk about this. Actually, let's summarize very quickly because it's going to be just one bit of change to make it resilient to that. So the first principles are, again, keep in mind what you do when you're on the phone with somebody speaking English in a bus. The error detection is the first one. So you have to figure out that there was an error. Otherwise, there's no way to tolerate errors, right? If you can't figure out. So you have to figure out that there was an error. Then you send feedback and ask for retransmission. So retransmission is another one. Okay? So you detect there was an error, ask for retransmission. If there's an error in the asking for retransmission, you also assume that there is a retransmission. You transmit again anyway, and that produces duplicates. How do we deal with duplicates? We use sequence numbers. So we add sequence numbers to packets so that we can detect when, on the receiver end now, we can detect when somebody sent the packet twice because they thought there was an error. Right. So now what about packet losses?
Sequence numbers. Sequence numbers.
Sequence numbers. Okay, let's explore this idea. So let's play the protocol. Okay, you play the receiver. I play the sender. Okay, so 1 block. Uh-huh. 2 ciao. Okay.
Now if I get something, if I get something like 4.
What's that?
If you say something like 4 and something like that, next I will answer you.
Right. Okay. Let's
I
do this.
didn't get the third one.
What do you do?
Do nothing because I get nothing.
No, you ask. Please repeat because you heard something. Okay.
I heard something. Yeah.
Well, okay. So you hear something. Please repeat.
Please repeat.
And I, for some reason, I don't hear the please repeat.
And next.
Huh? After a while, I'm playing the waiting game. After a while, a timeout is going to fire in my head. And it's going to say,
Did you say something? So effectively, the point is, if you tell me something, but that something gets dropped, how can you figure out that it was dropped? How can you distinguish a drop packet from silence?
Heartbeat.
That is a possibility. So, do you understand the term heartbeat? Heartbeat is there's always something going on in the channel. So somebody always sends. Okay? So I always send. There are some fillers in natural language, some fillers in the conversation. So when you, what I just said. What did I say? I said, serious, that is a filler. It's a noise that I produce to keep your attention up. Like that is going to be effective. No, because if I didn't do that, then you might fall asleep and or assume that, and then walk away. So I say a lot. That is effective. That is a possibility. But again, what if you don't hear the heartbeat? What do you expect?
Just wait it, buy time out.
So you're back to timeout. That was my point. So you don't hear the heartbeat, you're back to timeout. So the ideas are exactly the same. You need a mechanism to detect a loss, just like you needed a mechanism to detect an error. The mechanism to detect an error is an error detection code. What's the mechanism to detect a loss? A timeout. So the only thing you need is an extra mechanism, a timeout, to detect a loss. And then the protocol remains the same. Now instead of detecting an error, you say timeout goes on and goes off, and I resend. Okay, so without being too complex, here's the variant of that protocol that instead of just tolerating errors, it also tolerates losses. And it uses timeouts, no surprise. So the quick thing is, goes around. Actually, go back a second. The interesting thing is, remember the example, I tell you something and then I wait for you to react. You react, but I don't get it because information doesn't get through. What do? I assume that you said something and that it got lost. So a timer goes off in my head and I say something again to you. So that's it. This is it. This whole protocol. I mean, you can complete the loop yourself. This whole protocol is called stop and wait. Because again, I say something, I wait for you to say "uh-huh." If I don't hear it, I say it again, and so on. And actually, here's a quick question for you. What about the receiver? This is the sender side. Does the receiver change anything? No, because the receiver can't tell. I mean, at that point, it really cannot tell that the sender is silent because the sender sends something, or because the sender doesn't have to send anything. Okay, so in that case, there's no distinction. If the receiver times out, they might fall asleep, but there's no timeout. So the receiver is exactly the same. Oh, lost the part. Now, the second part is on the... Man, we have, 20 minutes or 25 minutes? Is that right?
Half an hour.
Half an hour. Beautiful. Okay, so is this efficient? The stop and wait efficient? No. Why?
We may try to send next phrase, to speak next phrase while waiting for the response.
Yes, exactly. So what if you were playing the stop and wait protocol with somebody on the moon? Couldn't, somebody on the sun maybe concerned with something else. So somebody on the moon. What is the latency between here and the moon? At least 1 second, right? About 300,000 kilometers.
So if you have a very, very fast network and you use stop and wait between here and the moon, you're very, very inefficient. Because you send one packet and then you have to wait for how long? 2 seconds. You have to wait for the information to get there and the reply to get back. Okay, the thing is called round trip time. Twice the latency. So how do we make it more efficient? We pipeline things. In order to understand these things, I'm going to go very quickly through this because I'm sure you all understand this. I'm going to characterize communication channels with these 2 numbers, latency and throughput. You all know that? Should I even... Okay. Latency and throughput, we can skip. Here's my nice animation. Latency is... latency. So, what's latency? Latency is the delta in time, the difference in time between the time the first bit enters the channel and the time the first bit exits the channel, the first bit of the message. And throughput is that other delta t, so it's the difference between the time it takes for the first bit to enter, last bit to exit minus the time the first bit exited, divided by the size. Okay, so it's bits per second. So the dimensionality of latency is time, the dimensionality of throughput is 1 over time, or bits over time, size over time. Okay, latency and throughput. Okay? The total transfer time for a message is typically the latency, because you have to pay that no matter what. So the latency is sort of the fixed cost. Because no matter how big the message, you have to pay latency. And then there's the variable cost, which is the cost that is inversely proportional to the throughput. So it's the size divided by the throughput. Okay? So you always pay those things. And these are examples. Again, I took these slides from one of the courses that I teach my undergraduates, and the example was with Zurich, so I changed it to St. Petersburg to be nice. So if you want to transfer a file, the 2 things you should be asking are, what is the latency, what is the throughput, what is the size of the file? And then you know that if it's a small file, then the time is dominated by the latency, typically. If it's a big file, the total transfer time is dominated by the size divided by the throughput. I'm not even going to go through this because we don't have time. The conclusion of this was, if you need to transfer 10 DVDs from Lugano to St. Petersburg, and you really need to be fast, and you also have a lot of money, take a plane. Because it takes a long time.
And also that you have to take 1 DVD without content.
But you can transfer all the DVDs in the same backpack and all the acknowledgements back in the same backpack. So take a return, a round trip. So back to this. What is the inefficiency of this? The inefficiency of this is that we go around the circle, and once we have gone, we go around the circle. Even if we go from here to here to here, okay, this is a round trip time essentially. We are only sent 1. And this is inefficient if you look at actually the timeline. So consider this to be the timeline, this is the sender and the receiver, and this is the usage of the channel. So all throughout this time, we are using the channel. How many bits do we actually send? Well, if we send a message, we initially send a message. This is the time where the first bit enters. So this is the latency. This is the time where the first bit of the message exits the channel. And then it goes like this. And then we have to wait for the acknowledgement. Acknowledgement is 1 bit only, so easy, goes back. So what's the utilization of this? And again, because this is a stop and wait, keep going. Sequence number 0, sequence number 1. And so we keep doing that, right? So how much are we actually using the channel in terms of how efficient are we in using it? Well, you have to measure the time that we use the channel versus the time that we're wasting time, right? And so those times are, my time's up. Those times are twice the latency. That's the transmission time size divided by throughput. And this is one round. This is one iteration. Okay. So this is the total time. And this is the actual time that we're transmitting. So the utilization factor is this divided by all of this. In this case, if this is a correct visual representation, would this be a good use of the bandwidth of the network? Mm-hmm. No, because as you can see, most of the time you see white. Okay. So white means that we're not using the network at all. We want to fill this as much as possible.
Depends on the size of the packet.
That's true. Absolutely. However, that
may be efficient. Why not?
It may be efficient. Absolutely. It may be very efficient. Exactly. Give me the size. Since you're so quick and smart. No. What is the size? What is the size that would make it perfectly efficient?
1.5K.
What's that?
1.5K. 1,500
gig.
1,500
bits. Oh, that's
not
it.
bad, at least.
He pulled it out of his Ethernet card. What's that I'm missing? Who's speaking? Oh.
The size might depend on the probability of that corruption.
Well, the more the size, the more.
Look at this picture. What did I tell you?
Exactly.
I told you.
The more the time, the more efficient it would be
in that model.
For a second, look at this picture. And now in this picture it's inefficient. Why? He correctly observed, because it's a small size. Compared to what?
Compared to latency.
Perfect. So the latency is what gives you the white space. Okay? So, well, all we have to do is to increase the size to fill the white space.
Or decrease the latency.
Or decrease the latency. True. Okay, so latency is 0, everything is super efficient. What would fill this? Well, the size of the packet that would fill the channel is twice the latency. Think of that dimensionally. I'm asking you for a size, and I'm giving you a time, a size, that the unknown, and a throughput, which is size over time. So, just by trying to match them up, it's the throughput multiplied by latency, right? Because this is size over time multiplied by time is size. Okay. That's how engineers do it. I'm not a mathematician, I'm an engineer. So, you give me two things, I try to put them together so that they fit. No, seriously, it's exactly that. It's twice the latency divided by, multiplied by the throughput.
Yep. But it doesn't work so well, because we have noise, and any resending will cost us more and more as we increase the size of the packet.
Okay. What I said is not completely true for a bunch of reasons, and hopefully we'll get to that. One is, yes, if there are errors, but errors are inevitable. It is true, you're absolutely right. If there's only 1 bit of error here, and we're sending 2 gigabytes, then the retransmission is going to have to be 1 gigabyte. So, absolutely, you're right. And the other thing is, still, in this case, if you pump the size as much as you want, you're still paying an empty space of 2L. So it's not that the efficiency is going to go to 1, right? So the trick is to do something that you, I think, hinted at before, right? And which is called pipelining. Meaning that, this was the utilization factor that you'll probably care about. So, I can, if I have this white space here, I can gamble. Okay? I can gamble and say, I'm going to assume that the packet went through. And I'm going to send another packet. So send another packet. But notice,